Hello students, welcome to the 7th lecture on the topic differential equation. So in this lecture we will cover up the second order linear differential equation. So let's begin. So till now we have covered up the first order differential equation and now we are in position to discuss about the second order linear differential equation. So this will be the content of today's lecture. So firstly I'll write down the journal form of the second order linear differential equation. So the journal form, so we call this equation as a journal form of the second order linear differential equation, and here px, qx and rx all are the functions of x. So I will write down, and these may be constant also. So we will discuss two cases when this rx is equal to 0 and when the rx is not equal to 0. So first, if rx is equal to 0, then we will call this equation, this I call it as equation number 1, we will call this equation 1 homogeneous differential equation. Okay, now if rx is not equal to 0, then we call 1 as non-homogeneous differential equation. What we have done, if you can observe that if my rx is 0 over here, then we call this as homogeneous. The equation 1 is called as homogeneous, and if rx is not equal to 0, then we will call 1 as non-homogeneous differential equation. So if I want to write down two cases, so I will say, and this one we will call it as is non-homogeneous differential equation, and we can say it as like HDE in the short form, and I'll call this as NHD in short form. So first of all, our focus will be on solving these type of differential equation, and afterwards when we are done with this, we will move on to solve this type of second order linear differential equation. So let's start with finding out the solution of this type of differential equation, that is homogeneous differential equation. Now before finding out the solution of the second order homogeneous differential equation, we must know few terminology, that is linearly dependent and independent functions and Wronskians. These two are important to describe the solutions of the differential equation. So let's see what do we mean by linearly dependent and independent functions. So I'll write down the heading. Okay, so what is this? We say that two functions fx and gx that are defined on closed interval AB are said to be linearly dependent if one is scalar or constant multiple of other. That is, if you can write one function as a scalar multiple of other, or you can write fx by gx is equal to some constant k, and here k is a constant. Otherwise, they will be called as the linearly independent function. If both the function cannot be written in this form, then we will say that the functions are linearly independent. Now we will take few examples to make it more clear. So example 1, suppose your fx is equal to x and gx is equal to 3x. Now we can see that they are linearly dependent. So why they are linearly dependent? Since I can write fx as a constant multiple of gx, or you can see that gx is equal to 3 times of fx. So this is what this is. These both functions will be linearly dependent. Now example 2, if I have my fx is equal to 1 and gx is equal to x. Now what are these? These functions are linearly independent. So why they are linearly independent? Because I cannot write fx is not equal to any constant of g of x, or fx by gx is not equal to any constant. So what will be my gx and fx? These are linearly independent functions. Now we will describe the Wronskians of the function. Now what is the Wronskians of the functions? Suppose you have two functions y1 and y2. Then the Wronskian of y1 and y2 is equal to the determinant of this matrix. So this is the Wronskian. Like if you find out the determinant, that is y1 y2 dash minus y1 dash y2 dash. So this is the Wronskian. Suppose that if you have three variables or three functions, so I'll write say y1 y2 and y3. So then the Wronskians are given as, so if you find the determinant, you will find out the Wronskian. Okay, so these two terms are very important for describing the journal solution of the homogeneous differential equations and also the non-homogeneous differential equations. So let us see how these two are useful. So I'll write the theorem. If y1 and y2 are any two solutions of homogeneous differential equation, okay, you know what is the meaning of homogeneous differential equations, and are linearly independent, then we have yg is equal to c1 y1 plus c2 y2 is the journal solution. This one will be the journal solution of the homogeneous differential equation. What is the homogeneous? I'll just write down the form. What is the homogeneous differential equation? This is y double dash plus px y dash plus qx is equal to 0. So I am talking about the second order linear differential equation. So you can see that I am saying that y1 and y2 are two linearly independent solutions. Okay, if these are two linearly independent solutions of this homogeneous differential equation, then their linear combination is the journal solution of the homogeneous differential equation. So that means that for writing out the journal solution of this equation, that is homogeneous differential equation, you need to find out two linearly independent solutions. So the main thing is that there may be many functions that are the solutions of the homogeneous differential equation, but if those two functions are linearly dependent, they do not contribute to the journal solution. We have to find out two solutions y1 and y2 that are linearly independent, and the combination of those will be the journal solution of the homogeneous differential equation. Now to find out whether these two are linearly independent or not, here comes the role of Wronskian, that it will help you to find out whether the two solutions which you are considering are linearly independent or not. So we will go one by one. First we will write one lemma that gives you one important result. So I'll just write down the lemma. So this is my lemma 1, which says that if y1 and y2 are any two solutions of homogeneous differential equation, let me call this homogeneous differential equation as equation A. So of homogeneous differential equation A on AB, this is on the closed interval AB, then their Wronskian, that is I can represent the Wronskian like this, I have already told, is either identically 0 or never 0 on AB. Okay, so let us prove this result. The proof is very simple. So just see that what is given. We have given that y1 y2 are the two solutions. So I'll just write of equation A, that is of equation y double dash plus pxy dash plus qxy is equal to 0. This is my equation number A, the same as before, and we need to show that Wronskian of y1 and y2 is either 0 or never 0 on A comma B. So you know that what is the Wronskian? Since Wronskian of y1 and y2 is equal to what? The determinant. I have already told you that this is a Wronskian. So this I'll just write down again. So now this I called it as equation number 1, and we begin by observing that if I find out the derivative of this w with respect to x, as these functions y1 and y2 are the functions of x, so I can differentiate dw by dx, which is y1 y2 double dash plus y1 dash y2 dash minus y1 dash y2 dash minus y1 double dash y2. So you can easily see that this will be cancelled out, and this is y1 y2 double dash minus y1 double dash, and since y1 and y2 are the solution, so it should satisfy this equation number A, since because I am saying that it is given that y1 y2 are two solutions of this equation A. So obviously if I put y1 y2 in this equation, it will satisfy the equation A. So let's see what we will get. We will get, then what we have y1 double dash plus px y1 dash plus qx y1 is equal to 0, and y2 double dash plus px y2 dash plus qx y2 equal to 0. So I'll call this as equation number 2, I'll call this as equation 3 and equation 4. Now if you multiply equation number 3 by y2, like I will multiply this equation with y2 and I'll multiply this equation with y1, so and subtract both of these, what will you get? You will get, so I'll just write down to make this clear that what I have done. Finally we will get y1 y2 double dash minus y2 y1 double dash plus px y1 y2 dash minus y1 dash y2 equal to 0. Now this implies that what? You can already see that my dw by dx is coming out to be this. Okay, so by equation number 2, what I can find, that my derivative of w with respect to x is this. So I can write this as dw by dx plus px into this one is my w is equal to 0. This I am writing as equation number 6, and this I got by using equation number 1 and 2. Okay, so now you can see that this is of linear form and where integrating factor is equal to this. Okay, so now what will be the solution? You already know that this is a type of first order linear differential equation. So what will be the solution? W is the dependent variable into the integrating factor is equal to integration of 0 times integrating factor plus of c. So this gives you what? This gives you W is equal to c e to the power minus px dx. Okay, so you got the expression of w in terms of exponential functions. So you can easily see that this term is never 0. Okay, so what is the case? The case is if c becomes 0 or c is not equal to 0. So if c is equal to 0, then what will you get? Then w is equal to 0, or w is identically 0 for every x belonging to a comma b. And the second is if c is not equal to 0, w is not equal to 0 for every x belonging to a comma b. So this was the thing which we want to prove, that if y1 and y2 are two solutions of the homogeneous differential equation A on this, then the Wronskian is either identically 0 or never 0 on the closed interval AB. So we have proved this. Now we will prove one another important lemma which shows that if y1 and y2 are linearly dependent, then their Wronskian will be 0. And if the Wronskian is 0, this means that y1 and y2 are linearly dependent function. So this is one important lemma. So let us write down lemma 2. Says that if y1 and y2 are two solutions of, this is again the same homogeneous second order differential equation on this closed interval AB, then they are linearly dependent on this interval AB if their, this is if and only if their Wronskian, that is I can write this means the Wronskian only, Wronskian that is equal to y1 y2 dash minus y2 y1 dash is identically 0 on closed interval a comma b. So let us prove this one. Again the proof is very simple, so let us prove. So now we have to prove two things. First of all, we will consider y1 y2 are two linearly dependent solution, and then we have to show that Wronskian is 0. Okay, and then we will consider that if Wronskian is 0, these two solutions are linearly dependent, because this implies this and this implies this. So let us see the proof. So for the first case, we will see that given y1 and y2 are two linearly dependent solutions of A. I'll call that homogeneous differential equation of second order as A, and we need to show that the Wronskian is equal to 0. So now let's see. Now you know that since Wronskian of y1 and y2 is equal to this, we have to show somehow that this will be equal to 0. So if y1 and y2, we have the information that y1 and y2 are linearly dependent. So there can be two cases again. That case one, that if y1 and y2 are already 0, like if y1 and or y2, any of the one can be 0, so then what will happen we will see. And if these both are non-zero, then what will happen we will see. So case 1, if y1 or y2 is identically 0 on a comma b, say y1 equal to 0. Now since you know that these are y2 is linearly dependent with on y2, and this also implies that y1 dash is equal to 0, and if you put here this y1 is 0 and y1 dash is 0 over here, you can see that the Wronskian is coming to be 0. So you can see that this implies Wronskian on y2 is equal to 0 for every x belonging to a comma b. Similarly, if my y2 is 0, this will same thing will happen, that the Wronskian will go to 0. And you know that if any of the function is 0, they are linearly dependent with any other function. So now what is the case 2 when both are non-zero? If both y1 is not equal to 0 and y2 is not equal to 0, so now we will see what will happen. So since y1 and y2 are linearly dependent, so what will happen, y2 will be equal to c y1, because these both are linearly dependent, where c is any constant. Okay, so this implies what will happen, y2 dash will be equal to c y1 dash. This is again one equation. I'll just differentiated this, so I will get this. So now what you can see, that if I see the value of Wronskian, what it comes out to be, mainly Wronskian is this. Okay, now just see the value, y1 is y1 and y2 dash is what, c y1 dash from this equation. I'll write this as equation number 1 for this lemma, and this is equation number 2. So from equation number 2 I can put y2 dash as this, and y1 dash and y2 from equation number 1 as cy1. Now you can see that these both are getting cancelled and this is equal to 0. So right now what you have proved, that if y1 and y2 are linearly dependent, what you are getting, you are getting the Wronskian is coming out to be 0. Now we will prove that what will happen if I have the information that Wronskian is 0, then y1 and y2 will be linearly dependent. So let given Wronskian of y1 y2 is equal to 0 to show y1 and y2 are linearly dependent. So now see, we have Wronskian. Wronskian is what? We can write the Wronskian. Again we are using the definition. This is y1 y2 dash minus y1 dash y2. And what we have from here, what we can write, this is equal to 0. So this will be equal to 0. Now see that I can divide this equation by y1 square, because y1 y2 both are non-zero. We have considered this y1 y2 and non-zero, and then we can see, if I divide the both side by y1 square, this will give me d of y2 divided by y1 is equal to 0. If you differentiate this, you will get this one, and this implies what, y2 by y1 is equal to some constant k, and this implies y2 is equal to some constant k y1. So you started from here and you came over here, and this implies what? This implies y1 and y2 are linearly dependent. And here this will hold for every, I wrote for every x belonging to the closed interval a comma b. So now you have seen that this hold true from two sides. That is, if you have shown that if these are dependent, then Wronskian is 0, and if Wronskian is 0, these both are linearly dependent. So this will help you to see whether you can write like you have two solutions y1 and y2, and if they are linearly independent, then only they will contribute to the general solution of the homogeneous second order differential equation. And if they are linearly dependent, you know how you can check that they are linearly dependent. If the Wronskian between two is coming out to be 0, then they are linearly dependent. So you have got only one function. You have to find another function which is linearly independent, then you can write out the general solutions for the homogeneous differential equation. Now I'll talk about little bit about non-homogeneous differential equation, but in this lecture we will concentrate only over the homogeneous differential equation. So I'll just write down one theorem. If yg is a general solution of homogeneous differential equation y double dash plus pxy dash plus qxy equal to 0, this you call it as equation 1, and yp is the particular solution of non-homogeneous differential equation y double dash plus pxy dash plus qxy equal to rx, call it as equation number 2, then the general solution of non-homogeneous differential equation 2 is yg plus yp. So what is the additional part in this? If you have rx over here, instead of having rx as 0, if you have a non-zero rx, right? So what will be the general solution? The general solution will be yg, that is the general solution for the homogeneous differential equation, and you have to add a yp. Yp is what? Yp is a particular solution of this non-homogeneous differential equation. Obviously we will see how to find this particular solution and general solution of homogeneous differential equation in the coming lecture, but now just understand that if you have a general solution yg, I have shown you that what will be yg? Your yg will be c1, this will be c1 y1 plus c2 y2, where y1 and y2 both are linearly independent. Linearly independent means the Wronskian should be non-zero, because we have already shown that if it is 0, then they are linearly dependent. So these both will be linearly independent. So this is the general solution for homogeneous differential equation, and you have to find out the particular solution for the non-homogeneous differential equation, and add these two, you will get the general solution for the non-homogeneous differential equation 2. So we will do everything one by one. First of all, let's see that if we know one solution, how can we find the other solution? So I'll just write down. So I'll write down the heading, using known solution to find another unknown solution. So here what is the condition? Like suppose that I want to find out the yg. Yg is a general solution of the homogeneous differential equation, and anyhow I know this y1. So how I can find out this another solution y2? So this is the problem we will discuss now. So consider, I'll just write down, consider a homogeneous differential equation. Again, I'll writing the same thing. Pxy dash plus qxy equal to 0. This say as equation number 1. So we have discussed that if y1 and y2 are two linearly independent solution, then y1 and y2 are the general solution of the homogeneous differential equation. Okay, so now the problem is, again I am telling what is the problem. If you know this one y1 and you don't know this one, so how can we find out the another solution with the help of the known solution? So let us see. Now we can write that y1 is known and y2 is unknown. So we want to find out y2. So let us take one assumptions, like let us assume, we assume that y2 is some function of y1. Okay, so this is let us assume that y2 is equal to some vx function is the solution of equation 1. This is my equation 1. And what we do, we will try to discover this unknown function vx. Okay, this is already known to us. Y1 is already known. So if somehow we discover this Vx, our problem will be solved. So let us see how we can discover this unknown function Vx. So if you differentiate this equation two times, like if I differentiate y2 once, I'll get, since these both are the functions of x, so first I'll differentiate this y1 and then I'll have this one. And if I differentiate this second time, what I'll get? Finally, I'll get this. Okay, now what you need to do is that you need to substitute this value and this value in equation number 1, because y2 is what we have assumed, that suppose that this y2 is the solution of 1. So what is the solution? That, like, what is equation number 1? This is my equation number 1, and since we have assumed that y2 is solution of this, so it must satisfy equation number 1. So I'll just write, we get, like after a few manipulation and rearrangement, what we will get? We will get Vy. Can do the calculation. These are simple calculations, and you will find out that I will get like this. Okay, now since y1 is the solution, this will go to 0. Since y1 is the solution, you can see that if y1 is the solution of this differential equation 1, that means that y1 will satisfy this equation 1. So what will happen to this term? This term will go to 0. So I will write, since y1 is solution of equation 1, my first term will be 0. Okay, so what I'll be left with? I'll left with this portion. So I will this implies that what I'll get v double dash y1 and v dash 2 y1 dash plus p y1 equal to 0, or I can write v double dash by v dash is equal to minus 2 y1 dash upon y1 minus p. And now integrating, what we will get? We will get log of v dash minus 2, and this implies my v dash will be y1 square e to the power minus p x. This is a function of x, so I'll get this. And now again integrating it, you will get the value of v, which was our main aim, to find the value of v. So now you have seen with the help of the known function how we can find out the unknown function. Now since v is known by this integral In this integral, obviously you know this quantity y1, and you already have this p. What you have to do, you have to just find the value of this, and what is our y2, we will get the second solution. What is our the second solution? This will be y2 is equal to vx into y1. So this is, now this is known. Okay, so this is how you will find out y2 when y1, or somehow you know one solution, how you can find the other solution. So let us do few examples on this. So example number 1, if y is equal to x square is one solution of my differential equation this, then find the other solution, and hence write the journal solution. Okay, so let us do this problem. So here we are given one solution. What is your aim? Your aim is to find out the another solution and finally write out the journal solution. So how will you do this type of problem? It's simple, that since you know y1 is x square, I will denote this as y1, and so y2 will, you have to consider what, this. Okay, this I call it as equation 1 and this I call it as equation 2. Now no need to do all the derivation. This derivation is not important from your exam point of view, only this formula is important. I have given the proof to make you more clear that how we are writing this formula. If I give this formula directly, you won't have understand that how this expression came. So what will be the Vx? Our Vx is 1 by y1 square. I have found it over here, this, and I gave you the proof also. So this dx into dx. So if I find this expression, I will find out the Vx and finally I will find y2. So let us see what will be my Vx. For my proof, I have considered my equation in this form, right? So here the coefficient of y double dash is 1. Just notice this. So what we have to do, we have to make our equations in the same way. That is, we will rearrange our differential equation this into the form from which we gave the proof. So I'll just write that x square y double dash xy dash minus 4y equal to 0, and since this changing given differential equation to the standard format or standard form, y double dash plus px y dash plus qxy is equal to 0. Here you can see that the coefficients of y double dash is 1 and here you have x square. So what you have to do, you have to first convert this equation into the standard form. So what will be, just you have to divide this by x square. So what will be the equation? This equation will be changed into this. Now you can see that here px is this and qx is coming out to be this. So px is this, implies that we need only px, that is 1 by x. And what will be our Vx? So let us find out Vx. So my Vx will be equal to integration. I have already my one solution, that is x square. So 1 by y1 square, that is x to the power 4 e to the power minus of px dx to whole integration. So you can easily see that this will be minus ln x, and this will be equal to, if I find out, this is my v of x, this will be, and this is equal to x to the power minus. So we got Vx as this. So now what will be our, hence our y2 will be what, Vx into y1. So we are getting Vx as this, and what will be our y1? Y1 is already given, that is x square. So this will be equal to 1 by 4 x square. Now here see, the constant term doesn't matter because it absorbs in the constant. Like if I ask you what is the journal solution, so what you will say, the journal solution is equal to c1 y1 plus c2 y2. So this is what, c1 y1 is what, x square, it is given, And right now you have found out what? Y2. So this is my Y2. This constant term can be absorbed in this. So these constant terms are not important. Even if you write y2 as 1 by x square, it's okay. So this will be equal to c1 x square plus c2 1 by x square. Now you can easily check that this is linearly independent. These both are linearly independent. I told you that we can write the general solution of homogeneous differential equations like this only if y1 and y2 are linearly independent. So you can easily check that these both are linearly independent by finding out the Wronskian. So we can see, I'll just show you that Wronskian of y1 and y2 is coming out to be what? So this is my, let me take the whole y2 and 2x. Okay, so now just find out the Wronskian. You will see that it is coming out to be this, and 1 by x is never equal to 0 for every x where 0 is not there. Okay, it is and for that, if it is 0, w is not defined. So this will be the general solution of differential equation for every x like I should delete 0 because here you can see that this will be not defined, and here also you can see that Wronskian is not equal to 0 for every non-zero x. So this is linearly independent, y1 and y2. So this will be my journal solution, or you can write this is your journal solution. So I'll just encircle this one, that this is your journal solution. Now we will do one more example. So it is given that if y, one of the solution, is e to the power x of this differential equation, then find the other solution, hence the journal solution. Obviously, if we find two linearly independent solution for the second order linear differential equation, the linear combination will give you the journal solution. So what will be the process? Since you know that you have one solution, it is given, and again you need to change this form into the standard form. So I'll just write the standard form. This will be by getting divided by x. So I put my differential equation this in the standard form, and here you can easily see that what will be your px. Your px will be this. So I'll just write down. Okay, and now you know that y2 is what? Vx into y1, where vx is what? Vx is this integral dx. Okay, so let us write down everything. So let us write down all the values and then integrate it. So this will be, and again we have to integrate this. So this implies that finally you will see that you are getting this simple expression, and now y2 will be what? This is my vx, so y2 will be what? Square by 2 into e to the power x. So therefore the journal solution is, what will be the journal solution? Yg c1 y1 plus c2 y2. This is equal to c1 e to the power x plus c2 x square e to the power x divided by 2, or you can just write c1 e to the power x plus some other constant x square e to the power x. This is your yj. Now again you can check that this y1 and this y2 are linearly independent. So we have written the journal solution of the homogeneous differential equation like this. So till now in this lecture what we have done, we have covered the homogeneous second order differential equations where one solution is known, but how can you find the other solution? In the next lecture we will see that how we can find both the solution, like even anything is not known, just how can you solve the second order linearly differential equations with the constant coefficients. So we will do those things in the next lecture. Thank you.